Ancient Egypt's master builders left behind a mystery carved in stone. They shaped immense blocks of granite, one of the hardest rocks on Earth, into objects of impossible precision. Yet history claims they did it all with simple, soft copper tools. This contradiction defies everything we think we know about ancient technology. By the end of this journey, you will discover the startling evidence that could rewrite our understanding of human history. We will uncover how a lost drilling method defies modern replication and examine if a legendary civilization possessed knowledge we have since forgotten. What does it take to truly erase an entire technology from human memory? Granite is a material that seems to laugh at the passage of time. It is an igneous rock born from molten magma that cooled deep within the earth over millions of years. This fiery origin under colossal pressure gives it a unique crystalline structure, a chaotic interlocking of minerals like quartz and feldspar. That structure is what makes it so brutally hard, ranking a 7 on the Mohs scale of mineral hardness. To put that in perspective, a common copper tool ranks only about a 3. It is the difference between trying to carve wood with a hard chisel and trying to shape a diamond with a piece of soft clay. Now look at what the ancient Egyptians achieved with this formidable material. In the Ramesseum, the mortuary temple of Ramses II, you will find the broken remains of a colossal statue. This single figure was carved from one block of granite and originally weighed over 1,000 tons. That is heavier than most modern military tanks. Then there is the Great Pyramid, specifically the King's Chamber. Inside rests a sarcophagus made of a single, immense piece of granite. Its exterior surfaces are flawlessly flat, and its inner corners are sharp, precise right angles. The precision is so exact that modern engineers struggle to explain how it was hollowed out so perfectly. The sheer scale of these objects is staggering, but it is their impossible precision that truly defies logic. We are not looking at rough-hewn blocks. We are examining artifacts with mirror-smooth finishes, complex geometric shapes, and intricate details that would be challenging to produce even with today's computer-controlled machinery. This is the heart of the granite conundrum. How do you create such perfection on a monumental scale with tools that, by every known law of physics and material science, should be utterly useless for the task? The official explanation begins to feel less like an answer and more like a placeholder for a truth we have yet to uncover. So we arrive at the official suspect in this ancient mystery, a metal we find in our pockets every day: copper. In the world of the pyramid builders, copper and its slightly harder cousin, bronze, represented the pinnacle of metalworking technology. This was the Bronze Age, and these were the hardest, most durable metals they were supposed to have had. Archaeologists have indeed uncovered the evidence, unearthing copper chisels, saws, and even tube-like drills from sites like Giza. These tools are real, they are authentic, and they are displayed in museums as the very instruments that built a civilization. But when you hold one, its weight feels insignificant against the scale of the work it supposedly accomplished. The fundamental problem becomes brutally clear when we put copper to the test against granite. Think of granite as a solid wall of microscopic diamonds, its quartz crystals locked together in an unyielding matrix. Now, think of copper as a stiff but ultimately soft piece of clay. When a copper chisel is struck against a granite surface, it does not bite in and carve out a neat chip. Instead, the energy from the blow has to go somewhere. The copper, being vastly softer, absorbs that force by deforming itself. Its edge mushrooms, flattens, and dulls almost instantly. You are not so much carving the granite as you are rapidly destroying your own tool. To even make a visible scratch, you would need to constantly stop, re-sharpen your copper blade, and resume your work, a process so inefficient it would make the construction of these monumental objects a practical impossibility. This is not a matter of skill or effort. It is a basic law of physics, a fundamental mismatch between a soft material and a brutally hard one. So if these simple copper tools are the entire answer, then the question only grows louder. How could something so soft be responsible for work that feels so impossibly hard? The tools we have found seem to tell only a small part of a much larger and far more advanced story. Faced with this physics-defying puzzle, mainstream Egyptology offers a solution grounded not in cutting but in crushing. The official explanation sidesteps the weakness of copper by introducing a harder accomplice, stone. Specifically, they point to dolerite, a type of basalt that is significantly tougher than copper. The proposed method is one of sheer, relentless force. Workers would have used fist-sized dolerite pounders, swinging them repeatedly to batter the granite surface. This wasn't a delicate carving process, it was a brutal act of destruction, pulverizing the crystalline structure grain by tiny grain. Imagine taking a hard hammer to a concrete sidewalk, chipping away minute fragments with every blow until you've slowly, painstakingly worn down a shape. After the rough form was pounded out, the theory suggests a second stage involving abrasives. Quartz sand, which is actually harder than the granite itself, would be poured onto the surface. Then, using a copper saw or a copper tube as a drill, workers would drag the tool back and forth or spin it while the sand did the real work. The copper itself becomes irrelevant. It's just a carrier, a way to press the truly hard material, the quartz sand, into the granite. The sand particles embed themselves into the soft copper and act like countless microscopic teeth, grinding the stone away in a slurry of dust and water. Modern recreations show this method does work. You can see videos of people using a copper tube, some sand, and water to slowly, over many hours, drill a hole into a granite block. A fine, circular groove appears, proving the technique is technically feasible. This is the core of the accepted theory. It is labor-intensive beyond comprehension, but it is possible. It relies on simple physics that we can replicate today, which is precisely why it remains the standard answer. But does proving something was possible also prove it was what actually happened? Or does this explanation, while logically sound, still leave gaping questions about the staggering speed and peerless precision the ancients achieved? This gap between what the theory says is possible and what the granite itself reveals is where we encounter the first major crack in the conventional story, the precision problem. We are not examining rough, pitted surfaces left by pounding stones. Instead, we see a level of exactness that borders on the microscopic. Take the unfinished obelisk in Aswan, a colossal monument that cracked and was abandoned in its quarry. This giant piece of stone is a frozen moment in time, a snapshot of ancient work in progress. Etched into its surface are the precise lines and markings the workers were following. More tellingly, areas that were partially finished show expanses of granite that are flawlessly flat, as if a massive, impossibly sharp plane had skimmed across the rock. How do you achieve a perfectly flat, polished surface across a 50-foot-long obelisk by violently pounding it with another rock? The very idea seems to defy the nature of the process. Then there is the Serapeum of Saqqara, an underground labyrinth containing 24 massive stone boxes. Each one is carved from a single, solid block of granite or diorite, another brutally hard stone. Their lids weigh many tons, yet they fit their bases with a seamless, airtight precision. But the true marvel is their geometry. The corners are not just roughly square, they are perfect right angles sharp enough to cut your hand. The surfaces are not just smooth to the touch, they are flat and polished to a degree that modern laser levels confirm with astonishment. Modern 3D scans of these boxes reveal surface tolerances and geometric perfection that would be expensive and difficult to achieve with our most advanced machinery today. Now try to picture the process of creating this with a pounding stone and sand. Imagine trying to carve the intricate, sharp inner corner of one of those granite boxes by swinging a hard rock. Every strike is chaotic, unpredictable. You are not slicing, you are pulverizing, to then refine that shattered surface into a mirror finish using nothing but sand and a piece of soft copper is a task of almost unimaginable tedium and skill. It is like trying to sculpt a perfect ice cube by smashing it with a hammer and then polishing it with a piece of wet cloth. The physics of the proposed method simply do not align with the evidence left behind on the stone. The artifacts themselves seem to be whispering that we are missing a crucial piece of the puzzle, a technology that allowed for control, not just brute force. If pounding and sanding were the only tools, where are the mistakes, the tool marks, the inevitable imperfections that such a violent and imprecise method would leave in its wake? Their near-total absence is, in itself, one of the most compelling pieces of evidence. The artifact's impossible precision is only half the mystery. The other half is the staggering speed at which this work was supposedly completed. Consider the sheer volume of granite involved in a project like the Great Pyramid. Historians estimate it contains well over 8,000 tons of this intractable stone, all of it quarried from Aswan, located over 500 miles to the south. Every single block had to be cut free from the living bedrock, shaped with incredible accuracy, transported down the Nile, and then perfectly positioned hundreds of feet in the air. This entire process for the whole pyramid is thought to have taken around 20 years. The math, when you apply the accepted methods, quickly becomes a nightmare. Let's take just one step, cutting a single granite block for the king's chamber using the pound and grind method. Modern experiments give us a rough baseline. Using a copper saw with quartz sand abrasive, the cutting progress is agonizingly slow, perhaps only a few millimeters per hour. To cut a block free from a quarry face, a task that might require making 2 deep cuts each a meter long, could take a single worker many months of relentless, back-breaking labor. Now multiply that by the thousands of blocks needed. The manpower required just for the quarrying phase alone would swell to unimaginable numbers, with armies of workers doing nothing but sawing and pounding stone day after day for decades. The logistical support to feed, house, and organize such a colossal workforce pushes the boundaries of what we believe an ancient civilization was capable of. The official timelines begin to feel impossibly cramped, as if we are trying to fit a century of work into a single generation. This is the scale problem in its rawest form. It's not just about whether a technique works in a lab experiment over a weekend. It's about whether that technique can account for the construction of the most massive stone structures on the planet within a human lifetime. The pound and grind method provides a possible answer, but when viewed against the mountain of granite that needed to be moved, it feels like trying to empty an ocean with a teaspoon. How could they have achieved so much with such perfection in so little time? The numbers themselves seem to be pointing toward a forgotten efficiency, a lost technology that turned an impossible task into a historical reality. The abrasive sand theory presents a clever workaround to the soft copper problem. It transforms the tool from a cutter into a mere delivery system for a harder substance. Think of it not as carving but as controlled erosion. The ancient craftsman would have taken his copper saw, a tool that would be useless on its own, and sprinkled a layer of quartz sand onto the granite surface. As he dragged the saw back and forth, the soft copper would actually allow the hard, sharp grains of sand to embed themselves into its own edge. The copper blade effectively becomes a host holding millions of microscopic cutting teeth. With the addition of water to create a slurry, this sand-laden blade would then grind its way through the stone, scraping away minuscule particles with each pass. This process, known as lapping, is undeniably effective. We use the same basic principle today with modern sandpaper, where abrasive grains glued to a flexible backing do the real work of shaping a surface. In the case of ancient Egypt, the specific abrasive used could have made a dramatic difference. While common quartz sand is hard enough, they might have had access to something even more effective like emery. Emery is a natural compound containing corundum, the same mineral that forms rubies and sapphires, and it ranks a 9 on the hardness scale, far superior to quartz. Using an abrasive this hard would have significantly accelerated the grinding process, turning a slow crawl into a more manageable walk. You can find modern demonstrations where a simple copper tube, some sand, and water are used to drill a clean, circular hole into a granite block. The evidence is right there on camera, a fine groove slowly deepening, proving that the method is not just a fantasy. It works, but does proving that a technique can create a groove also prove it created the perfection we see in places like the Serapeum? This is where the theory meets its limitations. The process of abrasive sawing or drilling is inherently messy and difficult to control with precision. The abrasive slurry acts like a liquid sandpaper, and it grinds away at everything it touches. Imagine trying to carve the sharp, perfect inner corner of a granite box using this method. The moment your copper tool, laden with abrasive, reaches that corner, it would begin to round it off, eroding the crisp edge. The very nature of a pliable, slurry-based process works against achieving the knife-sharp geometry we observe. Furthermore, achieving the mirror-smooth, flawlessly flat surfaces on the sides of those same boxes would require an astronomical level of patience and skill. You would have to ensure the abrasive was perfectly evenly distributed, with no rogue grains causing deeper scratches, and you would have to maintain absolutely consistent pressure and motion across a vast area. It is the difference between sanding a small piece of wood by hand until it is smooth, and sanding an entire hardwood floor to a perfect glass-like finish using only your palms. One is tedious but possible, the other borders on superhuman. The abrasive theory provides a credible mechanism for removing stone, but the artifacts left behind demand more than just removal. They demand a level of control and finesse that the slurry and sand method struggles to explain. If this was their primary technique, where are the telltale signs, the slight undulations, the rounded edges, the microscopic scratches running in every direction? Their absence speaks as loudly as the perfect surfaces themselves. This is where the mystery moves from the ancient quarries to the modern laboratory. Experimental archaeologists have taken up the challenge, attempting to silence the skeptics by proving the official theory with their own hands. One of the most dedicated figures in this field was Denis Stocks, who devoted years of his life to mastering the techniques of the ancient stoneworkers. He did not just read about copper tools, he forged them, he used them, and he pushed them to their absolute limits. His workshops became a living test of what was humanly possible. With painstaking effort, he learned to cast copper chisels and saws, then spent months and then years training himself to use them with quartz sand and water. The results were a mixture of profound insight and sobering reality. He demonstrated that yes, you can cut granite with a copper saw and sand. You can drill a hole with a copper tube. The method is undeniably feasible, but the process he documented reveals the staggering gap between possible and practical. A simple, shallow cut that you could make with a modern diamond blade in seconds would take Stocks hours of relentless, grueling work. The copper saws dulled rapidly, the abrasive slurry was messy and difficult to control, and the physical exertion required was immense. This was not a part-time job, it was a lifetime of specialized, back-breaking labor. The skills involved were not something 1,000 unskilled laborers could pick up in a season. Stocks himself estimated it would take an individual at least 5 years of constant practice just to become proficient with these simple-looking tools. His experiments prove the technique exists, but they also highlight its agonizing inefficiency. Watching footage of these modern replication attempts is both enlightening and frustrating. You see the slow, circular groove forming in the granite, a testament to human perseverance. But you also see the modern craftsman, muscles straining, drenched in sweat, pausing constantly to add more sand and water. The progress is measured in millimeters per hour, a pace that feels cosmically out of step with the mountain of granite that makes up the Giza Plateau. If this was the primary method, then the pyramid builders were not just skilled, they were masters of an art form that demanded superhuman patience and a scale of manpower that challenges belief. The experiments answer one question: can it be done, while raising another, more profound one: could it have been done like this, on the scale and with the precision we find etched in stone? The evidence from the workshop suggests a resounding maybe, but the evidence from the pyramids themselves continues to whisper of something more. Perhaps the most direct challenge to the modern replication attempts comes not from a grand pyramid, but from a small, broken piece of stone tucked away in a museum. It is a granite core sample drilled out over 3,000 years ago and discovered by the renowned archaeologist Flinders Petrie. This artifact is a fossilized moment of ancient machining, and its testimony is undeniable. The core itself is a cylinder of stone that was somehow drilled out of a solid block, but the process was interrupted and the core was snapped off, leaving it embedded in the hole. When Petrie examined it, he saw something that should not exist. Spiraling down the length of the granite core is a single, continuous groove. This is the ghost of the drill bit's path, a perfect impression of its cutting edge. The groove is clean, deep, and uniform, with no chatter or wobble. It looks less like something ground away by a slurry of sand and more like the mark left by a modern coring drill. But the real shocker is what this groove reveals about the drill's performance. Petrie carefully measured the spacing between the spiral lines. This spacing, known as the feed rate, tells us how far the drill bit advanced into the brutally hard granite with each complete rotation. His calculations were staggering. The ancient drill bit fed into the stone at a rate of about 2.5 millimeters per turn. Now compare that to the modern experiments using a copper tube and sand. In those tests, the feed rate is agonizingly slow, requiring hundreds, sometimes thousands of rotations to advance just a single millimeter. The ancient drill was biting into the granite at least 500 times faster than our best modern attempts to replicate their supposed method. This isn't a slight difference, it is a chasm. It is the difference between a gentle stream eroding a canyon over millennia and a power washer cutting through concrete in an afternoon. The core sample is not just an artifact, it is a data log, and the data it records points to a drilling technology of terrifying efficiency. So what kind of drill could achieve this? A simple copper tube, even loaded with the hardest sand, simply cannot generate that kind of cutting power without itself deforming under the immense pressure required. The force needed to make a copper tube bite that deep that fast would instantly collapse the tube or jam it solid. The evidence suggests something far more robust. The drill must have been a rigid, powerful tool, possibly using a diamond-tipped bit or some other ultra-hard abrasive fixed permanently to its cutting edge. Imagine a drill where the cutting teeth were not loose sand, but were bonded to the drill itself, like the diamonds embedded in a modern masonry saw blade. This would allow for immense downward pressure and clean, fast, controlled cutting. The perfect spiral groove without the random scratching of a slurry supports this idea. It implies a single, continuous, and incredibly hard cutting point moving through the stone with relentless, machined precision. This one broken piece of granite core stands as a silent monument to a forgotten science. It tells us that the pyramid builders were not just patient laborers with simple tools. They were engineers who possessed a drilling technology that, in at least this one specific way, outperformed our own recreations by orders of magnitude. The core sample does not just ask how they did it, it demands to know what we are missing. The broken granite core with its impossible spiral is not an isolated clue. It points toward a pattern, a signature of technology that we recognize from our own workshops. When we examine other granite artifacts under the unforgiving eye of a digital microscope, the evidence becomes even more startling. Scattered across the surfaces of sarcophagi and the faces of cut blocks are tool marks that look nothing like the random, chaotic scratches left by abrasive sand. Instead, we see long, perfectly parallel grooves, as if a giant saw with multiple, fixed teeth had been dragged through the stone in a single, relentless pass. The consistency is machined. These are not the meandering paths of a handheld copper blade wobbling under pressure. They are the marks of a stable, powerful cutting system. Compare these ancient grooves to the marks left by a modern diamond-tipped saw blade. The resemblance is uncanny. Our diamond blades work by having industrial diamonds, the hardest substance on Earth, permanently bonded to a steel blade. As the blade spins at high speed, these fixed points grind a clean, straight path, leaving behind those characteristic parallel striations. The ancient marks show the exact same pattern, suggesting their tool also used a fixed, ultra-hard abrasive in a rigid, guided motion. Then there are the drill holes. We find them in granite and basalt, perfectly circular and often tapering slightly. Inside these holes, just like on the core sample, we see that same, impossibly fast spiral groove. A modern core drill used to create holes in concrete or stone leaves an identical signature. It is a hollow cylinder with diamonds embedded on its cutting edge, and as it spins and presses downward, it cuts a clean ring and leaves a central core. The ancient Egyptians, it seems, were using a near-identical process. This is the bedrock of the alternative theory, a theory that dares to suggest the builders of the pyramids possessed a form of machining. The term does not necessarily mean they had electricity or steel, but it does imply a level of mechanical advancement far beyond simple hand tools. It suggests they had devised a way to mount their cutting tools on stable frames, to apply immense and consistent pressure, and to achieve a rotational speed and power that we simply do not associate with the Bronze Age. They may have used a different power source, perhaps a complex system of weights and pulleys or water-driven mechanisms, but the outcome, as recorded in the stone itself, speaks a language we understand all too well. It is the language of precision engineering, so we are left with a profound disconnect. The official toolbox contains soft copper and pounding stones, but the stone itself bears the fingerprints of what looks like diamond-tipped saws and powerful core drills. One of these pictures is wrong, or more intriguingly, our understanding of the ancient world is desperately incomplete. The stones are not just silent monuments, they are talking. They are telling us how they were made. The only question is, are we ready to listen? But this evidence of machining leads to an even more profound and controversial question. Where did this knowledge come from, and where did it go? If the pyramid builders possessed technology that we struggle to replicate even today, why does our history show only simple copper tools? One radical theory proposes that the dynastic Egyptians were not the original inventors but the inheritors. They may have been the caretakers of a science left behind by a much older and far more sophisticated civilization that was lost to time. This is the lost technology hypothesis. It suggests that a precursor culture, perhaps even the legendary Atlanteans described by Plato, achieved a high level of technological advancement before some cataclysmic event wiped them from the historical record. Their surviving knowledge was then passed down and used by the early Egyptians, who eventually forgot the original science and were left only with the simpler, more laborious methods we associate with them today. This idea is not just speculative fiction. It is supported by serious researchers who point to geological evidence that challenges our entire timeline. The most famous example is the Great Sphinx of Giza. Mainstream Egyptology dates the Sphinx to the reign of the pharaoh Khafre, around 2,500 years before the Common Era. But geologist Robert Schoch, working with researcher John Anthony West, examined the erosion patterns on the Sphinx and its enclosure. He did not see erosion caused by wind and sand, which creates sharp, vertical profiles. Instead, he saw deep, rolling, vertical fissures that are characteristic of one thing: water. heavy, prolonged rainfall. The problem is, the Giza Plateau has been a hyper-arid desert for at least the last 5,000 years. To create that kind of water erosion, the Sphinx would have to be much, much older, dating back to a time when the climate of Egypt was radically different, perhaps as far back as 7,000 or even 10,000 years. This would place its construction thousands of years before the rise of the dynastic Egyptians. If the Sphinx is that old, then who built it? This single question shatters the conventional narrative. Researchers like John Anthony West and Robert Bovell have argued passionately that the entire Giza complex, including the pyramids, could be part of a vast, ancient astronomical map aligned to the stars of a much earlier epoch. They propose that the dynastic Egyptians found these magnificent, already ancient structures and simply adopted them, building their own smaller pyramids and temples around them, while the original, advanced building techniques slowly faded from memory. The tools we find in the archaeological record from the time of the pyramids, the simple copper chisels and stone pounders, might not be the tools that built the most precise and massive monuments. They might be the tools of a later people trying to maintain and replicate the works of their gods, the original masters of stone. The lost civilization theory remains fiercely debated, but it forces us to confront a haunting possibility. Our history might not be a simple, linear progression from primitive to advanced. It might be a cycle with ages of brilliance rising and falling, leaving behind only their most durable creations as riddles for those who come after. Another possibility emerges from the very air itself, the idea that the ancients commanded sound to command stone. This is the sonic or vibration theory, a concept that suggests the pyramid builders used specific, powerful, resonant frequencies to soften granite, making it temporarily pliable like clay. Imagine the granite's rigid crystalline structure, that unyielding network of interlocking minerals, being subtly manipulated by a precise hum. The theory proposes that these targeted vibrations could have reduced the internal friction between the mineral grains, or even caused the stone to enter a temporary state of acoustic fluidization, allowing it to be shaped with astonishing ease. It would be like a skilled singer hitting the exact note to shatter a glass, but in reverse, using the sound not to break, but to gently persuade the stone to yield. We find intriguing echoes of this idea scattered through ancient texts and myths, as if a faint memory of this science was preserved as legend. Stories from various cultures speak of master builders who used chants, trumpets, or sacred words to make stones move into place of their own accord. An Egyptian myth describes the god Thoth, the patron of knowledge, using the power of his voice to lift and position massive blocks. While these are myths, they often serve as vessels for lost truths, a way to encode advanced knowledge in a form that could survive across millennia. Could these tales of magical sounds and levitating stones be a poetic retelling of a real, and now forgotten, acoustic technology? Modern science offers a startling glimpse into how this might have worked. Researchers today are experimenting with acoustic levitation, using precisely controlled sound waves to lift and manipulate small objects in midair. The principle of resonance is a fundamental force of nature, where an object vibrates with maximum amplitude when exposed to its specific natural frequency. We see this when an opera singer's voice can crack a crystal glass. Now, apply that concept to the complex crystalline structure of granite. If the ancient engineers could discover the fundamental resonant frequency of a swan granite and project it with immense power, they might have been able to induce a state where the stone lost its rigidity just for a moment. In that window of time, shaping a perfect surface or making a precise cut would become a task of minimal effort. The hard stone would behave more like stiff putty, allowing tools to sink in and mold it without resistance. This would elegantly solve the twin mysteries of precision and speed. A softened block of granite could be planed to a flawless, glassy finish with a simple straight edge. Intricate holes and sharp inner corners could be carved with stunning accuracy because the stone itself was cooperating, its hard edges rendered temporarily malleable. The exhausting, month-long process of pounding and grinding would be replaced by a process that was almost gentle, a kind of sonic sculpting. The absence of chaotic tool marks and the presence of those machined-like parallel grooves could be the signature of a tool gliding through acoustically softened stone. If such a technology existed, it would have been the ultimate secret of the master builders, a power that made the impossible seem effortless. And its disappearance from history would be the greatest loss of all, leaving behind only perfect stone boxes and silent, echoing chambers where a powerful hum once rang. Sound is not the only invisible force that could have tamed the stone. Another theory emerges from the world of chemistry, suggesting the ancients possessed a secret formula, a liquid solution that could temporarily soften granite's unyielding surface. Imagine a potion brewed from rare plants or specific minerals that, when applied to the stone, would cause its hard crystals to become soft and pliable, like wet clay ready for the potter's hand. This chemical softening theory pushes us to look beyond tools and machinery into the realm of ancient alchemy. Could the master builders have been master chemists as well? We find faint clues in obscure papyri and long-forgotten alchemical traditions that speak of powerful solvents and stone-softening liquids. While no direct recipe for granite softening has been found in an Egyptian text, there are persistent legends and later Arabic manuscripts that describe mysterious fluids capable of dissolving or cutting stone with ease. These stories might be exaggerations, but they could also be distant echoes of a real and highly guarded technical knowledge. The practical science behind this idea is surprisingly solid. We know that certain acids can indeed attack granite. Hydrofluoric acid, for instance, is used today to etch designs into glass and stone. It reacts violently with the silica that forms granite's quartz crystals. Even milder organic acids, like those found in strong vinegar or from certain fermented plants, can slowly dissolve mineral bonds over time. The key to the theory is not a slow erosion, but a rapid, controlled reaction. What if the ancients discovered a specific compound, perhaps a blend of plant sap and mineral salts, that created an exothermic chemical reaction upon contact with the stone? This reaction wouldn't melt the granite, but it could severely weaken the microscopic bonds between the mineral grains. For a crucial window of time, perhaps just minutes, the granite's surface would lose its legendary hardness. In this softened state, the stone would be vulnerable. A copper chisel, utterly useless on hard granite, could then sink deep into the material, carving out precise chunks with minimal effort. A saw blade could glide through it, leaving behind those clean, parallel grooves we find, because it was cutting through a material that had temporarily lost its resistance. This would explain the impossible precision. To create a perfectly flat surface, a worker would simply apply the solution, let it work its magic, and then run a straight-edged blade across the stone to skim off a perfectly even layer. To carve a sharp inner corner, they would apply the chemical locally and then neatly carve out the shape before the stone rehardened. The process would be clean, controlled, and incredibly efficient, turning a year-long project into a matter of days. The evidence for this would be subtle. We wouldn't find giant vats of the chemical, as it was likely mixed in small batches for immediate use. But we might find traces of unusual mineral residues on the surfaces of finished granite artifacts, a chemical fingerprint waiting to be discovered by the right scientific instrument. The chemical theory provides an elegant, almost magical solution to the mystery. It suggests the Egyptians did not conquer granite with brute force, but with brilliant intellect, using a forgotten science that turned the hardest stone into the most obedient material. One theory shatters the very idea of carving altogether. Proposed by materials scientist Joseph Davidovits, the geopolymer hypothesis is a true game-changer, suggesting the ancient builders never fought the granite at all. Instead of wrestling with impossibly hard stone, they might have mastered a form of chemistry, creating an artificial granite that they could pour into molds like concrete. This is not about moving multi-ton blocks, but about mixing a sophisticated slurry and casting the pyramids in place. The science behind it is both simple and brilliant. Imagine taking the granite itself, crushing it into a fine powder from a much softer source stone. This powder, rich in silica and alumina, would then be mixed with a powerful alkaline activator. Think of it as an ancient industrial glue, a substance derived from natron, the same salt used in mummification, or from plant ashes. When this alkaline liquid meets the crushed stone powder, a chemical reaction called geopolymerization begins. The mixture heats up, and over a short period it recrystallizes, fusing into a new, solid stone that is chemically and physically almost identical to natural granite. This would solve so many mysteries at once. The flawless, seamless joints between blocks where a razor blade cannot fit become easy to explain. They were poured against each other. The complete absence of tool marks on vast, flat surfaces makes perfect sense. The surfaces were molded, not ground or pounded. The intricate, sharp-angled geometry of the granite boxes in the Serapeum would no longer require superhuman carving skill, just a perfectly crafted wooden formwork. The theory elegantly bypasses the entire problem of quarrying, transporting, and lifting monolithic stones, replacing it with a process of mixing and pouring that seems almost within reach of an ancient civilization. Yet for all its elegant solutions, the geopolymer theory faces a mountain of its own criticisms. Geologists point to the specific mineralogy of the Giza stones, showing crystalline structures that appear to have formed under immense heat and pressure over millions of years, not in a quick chemical reaction. They argue that the blocks show clear evidence of being quarried, with natural bedding planes and fossil inclusions that run continuously through the stone, something that would be impossible to replicate in a cast block. Critics also ask a devastatingly simple question: where is the evidence of the industry? To cast the millions of tons of stone in the Great Pyramid, you would need colossal factories for crushing rock, vast vats for mixing the slurry, and a complex delivery system to get this heavy, quick-setting material to the top of the growing structure. Archaeologists have found no trace of such an immense production infrastructure. There are no giant mortars and pestles, no mountains of crushed stone waste, no chemical residue on the scale required. The geopolymer idea offers a seductive escape from the problems of physical labor, but it introduces a whole new set of puzzles about chemical industry and logistical evidence that remains stubbornly missing. It forces us to choose between two equally challenging narratives, one of impossible stoneworking and another of a lost chemical technology that vanished without a trace. The debate over geopolymer theory hinges on evidence that can be seen, touched, and analyzed under a microscope. On one side, researchers like Davidovits point to features that seem to defy natural stone. They highlight the uncanny smoothness of certain surfaces, a finish so uniform it appears molded rather than carved. More compellingly, they point to the presence of tiny air bubbles trapped within the stone, a classic signature of a poured material like bubbles in an ice cube. Laboratory analyses have also identified unusual concentrations of specific minerals and organic compounds in some pyramid stones, substances you would not expect to find in natural limestone but which could be remnants of an ancient chemical binder. This, for proponents, is the smoking gun, the chemical fingerprint of a lost concrete formula. Yet the opposition has its own powerful arsenal of facts. They direct our gaze to the granite quarries of Aswan, where the evidence of physical extraction is carved into the landscape itself. There, you can still see the precise channels cut around the famous unfinished obelisk, a monument clearly being freed from the living bedrock, not mixed in a vat. The quarries are littered with the debris of this process, with broken tools and massive, partially detached blocks that tell a story of cutting, prying, and lifting, not pouring. When geologists examine thin slices of the pyramid's granite under a polarizing microscope, they see the telltale crystalline structure of igneous rock, with interlocking minerals that formed under immense geological pressure over millions of years. This complex, chaotic crystal lattice is something modern science cannot replicate in a geopolymer. A cast stone would have a much more uniform, amorphous structure. How could a chemically cast block perfectly mimic the unique billion-year-old history of a natural stone, complete with its specific fossil inclusions and mineral veins? The critics argue it simply could not, so we are left at an impasse, a scientific stalemate where each piece of evidence is met with a counter-argument. The air bubbles could be natural vesicles from the stone's volcanic origin. The unusual chemicals could be contamination from millennia of groundwater seepage, or even from the modern cement used in early restoration attempts. The smooth surfaces remain a mystery, but not one that definitively proves casting over an advanced and now lost method of polishing. This is not a clean puzzle with a single missing piece. It is a clash of two entire worldviews, one where the ancients were alchemical geniuses who mastered stone at a molecular level, and another where they were engineering titans who conquered stone with a physical prowess we can scarcely comprehend. The stones themselves hold the answer, but their testimony, written in mineral and crystal, is still being translated. Even if they possessed a secret method to carve granite with ease, the sheer act of moving these titans presents a puzzle of its own. To understand the scale of this challenge, we must travel to the sun-scorched quarries of Aswan. Here lies the unfinished obelisk, a behemoth of cracked granite that would have stood 137 feet tall and weighed nearly 1,200 tons. It is a fossilized disaster, but also a perfect textbook, showing us the very first step of the process. The channels cut around it are just wide enough for a man to stand in, demonstrating how workers used simple tools to painstakingly separate the stone from the bedrock. Once freed, the real magic, or the real back-breaking labor, began. The conventional explanation for transport is a symphony of primitive but effective engineering. A massive block would be levered onto a heavy wooden sledge. Then, armies of laborers would pour water onto the sand in front of this sledge, creating a slick, hard-packed surface that dramatically reduced friction. Teams of men, sometimes numbering in the hundreds, would then pull on great ropes, dragging the sledge and its impossible cargo toward the waiting waters of the Nile. For the final leg of the journey, these stone giants were loaded onto specially built colossal barges. The river itself became their highway, floating them northward with the current toward the construction sites. This entire process, from quarry to river to monument, is a masterpiece of organization and brute force. We can see it in our mind's eye, and it feels plausible for blocks weighing 10 or 20 tons. But the mystery deepens when we consider the true heavyweights, the granite beams in the King's Chamber above the Great Pyramid weigh between 50 and 80 tons each. The colossal statues and obelisks push the scale into the hundreds of tons. Can you truly imagine a wooden barge built in the Bronze Age, stabilizing an 80-ton block of granite in the shifting currents of the Nile without capsizing? The physics of loading that weight onto a boat without cranes or docks becomes a terrifyingly delicate operation, and the land-based journey becomes even more fantastical. Dragging a 50-ton block on a sledge is one thing, but what about the 1,000-ton stone foundation blocks at the Valley Temple, or the proposed weight of the completed unfinished obelisk? At those scales, the very ground would compress and fail under the pressure. Wooden sledges would splinter into kindling. The number of men needed to pull it would be so vast they could not all fit on the path ahead. The known methods, while brilliant, seem to strain and buckle under the weight of the largest artifacts. This logistical nightmare forces us to ask if we are missing another piece of the puzzle, a lost technique for making stone not just soft to carve but almost weightless to move. Were the master builders not just chemists and sonic engineers, but also masters of a forgotten physics that allowed them to defy gravity itself? Granite's impossible hardness was not a flaw to the Egyptians, it was the entire point. They chose this most stubborn of stones for a profound reason. one that transforms the mystery from a technical puzzle into a spiritual one. This material was far more than just a durable building block. It was a sacred substance, deeply intertwined with their core beliefs about the cosmos and the afterlife. Granite was intrinsically linked to the sun god Ra, the supreme deity who sailed his solar bark across the sky each day and through the perilous underworld each night. Just as Ra was eternal and indestructible, so too was granite. Its fiery, volcanic origin mirrored the sun's own creation from the primordial mound, and its incredible durability promised to withstand the ravages of time itself. To construct a pharaoh's tomb or a temple wall from granite was to build with a piece of the sun's own power, creating a permanent, unshakable bridge between the mortal world and the divine. This symbolism explains the obsessive drive to master this material. When a pharaoh was laid to rest in a sarcophagus of flawless granite, it wasn't merely for protection. It was a magical act, a ritual designed to ensure his soul would be reborn and ascend to join Ra, just as the sun is reborn with every dawn. The stone was a physical prayer for eternity. This context makes the impossible effort seem not just logical but necessary. The staggering investment of time, the back-breaking labor, the pursuit of perfection that defies our understanding, all of it starts to make a different kind of sense. They weren't just building a tomb, they were building a machine for resurrection, and only the most eternal stone would suffice. The choice of granite was never about convenience, it was about cosmic necessity. This spiritual imperative forces us to reconsider the entire endeavor. Perhaps the methods they used were not just practical technologies, but sacred ones as well, processes as deeply ritualized as they were mechanical. The perfection of the stone was a reflection of the perfection they sought for the soul within. The granite conundrum of Egypt is not a solitary whisper from the past, but part of a global chorus. Scattered across the globe are other ancient sites that echo the same impossible precision, carved in stone just as hard and just as perplexing. High on the Bolivian Altiplano, at a place called Puma Punku, lies a field of shattered andesite blocks that defy simple explanation. Andesite is a volcanic rock, a close cousin to granite in its formidable hardness. Yet these blocks are not rough-hewn monuments. They are precision-cut components, some with complex geometric shapes, interlocking channels, and razor-sharp edges that look less like stonework and more like parts of a colossal machine stamped out by a giant press. The surfaces are flawlessly flat, the corners are perfect right angles, and the repeating patterns suggest a level of standardization we associate with mass production, not Bronze Age craftsmanship. Then travel to the mountains of Peru, to the Inca sites of Cusco and Sacsayhuaman. Here, the mystery takes a different form: polygonal masonry. Enormous blocks of granite and limestone, some weighing hundreds of tons, are fitted together in a dizzying jigsaw puzzle wall. The stones have multiple, complex angles and bulging sides, yet they lock together so perfectly that you cannot slide a single piece of paper between them. There is no mortar holding them in place, only the genius of their geometry and the inconceivable precision of their cuts. These are not just stacked rocks, they are stones that have been shaped to embrace their neighbors with an intimacy that seems to defy physical law. The uncanny similarity between these sites, separated by vast oceans and supposedly unconnected cultures, forces a profound question. Are we looking at the independent invention of similar, highly advanced stoneworking techniques by different peoples who never met? Or does the presence of such parallel, physics-defying work hint at a shared, and now lost, source of knowledge, a common technological thread that once wove its way across the ancient world? The stones of Puma Punku and the walls of Cusco do not offer easy answers, but they amplify the question first asked by the granite of Egypt, suggesting that our puzzle is far larger and far deeper than we ever imagined. This obsession with perfect geometry reveals a mind that saw the world through numbers. The Egyptians' known mathematical toolkit was both elegant and practical, centered on the concept of the seek. This was their unique method for calculating the slope of a pyramid's sides. The sect wasn't an abstract angle measured in degrees, it was a tangible ratio, a specific number of palms and digits of horizontal run for every single cubit of vertical rise. It was architecture reduced to a workman's blueprint, a set of instructions that could be followed with simple measuring rods and strings to ensure that every single block from the base to the capstone contributed to that iconic soaring shape. This system demonstrably worked, and it speaks to a culture that had mastered the practical application of geometry on a monumental scale. But the precision we find locked within the granite itself, those mirror-smooth surfaces and perfect right angles, seems to whisper of a mathematics that went far beyond simple slopes. The creation of a perfectly flat plane across a 50-ton sarcophagus lid is a problem in three-dimensional space, requiring an understanding of surface geometry that feels startlingly advanced. How do you verify such flatness without modern lasers? How do you ensure that two opposing faces of a colossal granite box are perfectly parallel to within a fraction of a millimeter? The tools we attribute to them, the simple cubit rod and knotted cords, seem inadequate for achieving this level of micro-precision. This gap between their known tools and their achieved results fuels the theory that their mathematical knowledge was far deeper than what was recorded on surviving papyri. Perhaps the most compelling connection lies not just in the shape of the stones, but in their celestial placement. Some researchers propose that the granite elements within the Great Pyramid were not placed randomly. The king's chamber, built entirely from immense granite blocks, sits at a very specific point within the pyramid's core. Theorists like Robert Bovell have suggested that the entire Giza complex is a terrestrial map of the stars in Orion's belt, with the pyramid's layout mirroring the celestial arrangement. In this grand scheme, the granite chambers are not just rooms, they are focal points of cosmic energy, aligned with the passage of specific stars or the solstice sun. The stone itself, eternal and unyielding, becomes a permanent anchor, tethering the pharaoh's soul to the timeless cycles of the heavens. This transforms the entire endeavor from mere construction into a form of sacred astronomy, where every block, every angle, and every ton of granite was a single digit in a sprawling equation written in stone, an equation designed to unite the earth with the cosmos. While the theories are compelling, they remain trapped in the realm of possibility. To find proof, we must turn from grand speculation to microscopic detail, using the tools of 21st century science to interrogate the stone itself. Laboratories around the world are now subjecting these ancient granite artifacts to a battery of non-destructive tests, searching for the faintest ghost of a tool mark or a chemical whisper of the method used. X-ray fluorescence scanners are passed over the surfaces, not to see the stone, but to understand its elemental composition. This technique can detect the faintest traces of foreign metals, perhaps a residue from a long-vanished copper saw or the unique signature of a harder, unknown alloy. Scientists are looking for an elemental fingerprint that should not be there. At a much higher magnification, scanning electron microscopes reveal a world invisible to the naked eye. They can map the microscopic topography of a cut surface in stunning detail. The question is, what do these tiny landscapes tell us? Do we see the random, chaotic scratching left by a slurry of loose abrasive sand, with grooves running in every direction like a child's scribble? Or do we find the long, perfectly parallel striations that are the hallmark of a fixed, rigid cutting tool, like a diamond-tipped saw blade? This is not guesswork, it is forensic analysis. The very atoms of the stone are being asked to testify. Researchers are also employing spectroscopy to hunt for chemical residues. If the ancient workers used a chemical softening agent, its molecular signature might still be clinging to the granite, trapped in the microscopic pores for thousands of years. Finding an unusual concentration of an organic acid or a specific mineral compound on a finished surface, but not on a rough quarry face, would be a revolutionary discovery. It would shift the entire debate from how they moved the stone to how they persuaded it to soften. These scientific investigations are our best hope for moving beyond the stalemate between established theory and radical speculation. The stones have held their secret for millennia, but light, electrons, and molecular analysis are a new kind of key. The data now being collected in labs may soon provide the first hard evidence in this ancient mystery, revealing not just what was possible, but what actually happened in the workshops of the pyramid builders. This enduring mystery has not been ignored by modern storytellers. It has become a central pillar of pseudo-archaeology, a genre that thrives on the gaps in our historical knowledge. Television shows like Ancient Aliens have built entire franchises around the granite conundrum, presenting a compelling but deeply flawed narrative. They often leap from a legitimate question like how the granite core was drilled directly to a sensational conclusion such as alien laser tools. The dramatic reenactments and authoritative-sounding narrators can make these ideas feel tantalizingly plausible, blurring the line between entertainment and documentary. The problem is not that they ask how, but that they ignore the vast middle ground of human ingenuity in favor of extraterrestrial intervention. They present a false choice that either the Egyptians did it with the simple tools we've found, or they had help from visitors from another world. This completely bypasses the most fascinating possibility of all, that an ancient human civilization developed sophisticated and now lost technologies of its own. So why is this narrative so powerfully appealing even when the evidence is thin? It taps into a deep-seated human desire for a more mysterious and wondrous past. The idea that our ancestors were simple people with primitive tools can feel somehow diminishing. The notion of a lost golden age or of celestial teachers is far more romantic. It transforms cold, hard stone into a prop in a cosmic adventure story. This appeal is understandable, but it comes with a real cost. By attributing these achievements to aliens, we inadvertently rob our own ancestors of their full credit. We dismiss the potential for a human intelligence so advanced and so different from our own that we struggle to even recognize its footprints. The real mystery is not whether beings from another star shaped the granite, but whether we have forgotten a chapter of our own human story. A chapter written not in papyrus, but in the most durable library on Earth, stone itself. The next time you see a dramatic claim about ancient astronauts, ask a simple question. Is this explanation built on solid evidence, or is it simply filling a silence with a satisfying sound? But before we rewrite the history books, we must listen to the other side of the debate. The academic establishment, the Egyptologists who have dedicated their lives to studying this civilization, offer a powerful and grounded rebuttal. They do not deny the awe-inspiring nature of the stonework, but they challenge the leap to lost technologies. Their argument rests on a foundational principle of science and logic called Occam's razor. This principle suggests that the simplest explanation, the one requiring the fewest new assumptions, is usually the correct one. In this case, the simplest explanation is that the ancient Egyptians used the tools and methods we have actually found in their archaeological record, combined with immense skill and patience, rather than invoking a completely unknown and advanced technology that left no direct evidence behind. They point to the cumulative weight of evidence. We have found the copper chisels and saws. We have found the dolerite pounders. We have found quarries with partially extracted blocks that show clear chisel and channel marks. We have ancient diagrams and texts that reference these tools and the organization of labor. This is a cohesive, physical trail of evidence that fits within our understanding of a Bronze Age society. The alternative theories, they argue, require us to believe in a technology so advanced it could soften stone with sound or chemistry. And yet this technology somehow vanished without a single detailed description, without a single tool fragment beyond simple copper, and without a single mention in the extensive records the Egyptians kept about their lives and achievements. Where is the hard evidence for diamond-tipped drills? Where is the recipe for the stone-softening potion? where is the machinery for acoustic levitation? The burden of proof, they insist, lies with those making the extraordinary claim. A fascinating artifact like the granite core is not, in itself, proof of a lost machine. It is an anomaly, a puzzle that we have not yet fully solved within the context of the known methods. Perhaps the ancient craftsmen used a specific type of fixed abrasive we haven't yet identified, or a mechanical advantage we have underestimated. The absence of a perfect modern replication does not mean the official theory is wrong. It may simply mean we have not yet mastered the exact technique, the specific rhythm and skill that took a lifetime for an ancient artisan to learn. The mainstream view is not a stubborn refusal to see the wonder, but a disciplined insistence on following the evidence we actually have, not the evidence we wish we had. It is a reminder that human ingenuity, when applied with relentless focus over generations, can achieve results that look like magic to those who have forgotten the power of patience and cumulative knowledge. The true mystery from this perspective may not be a forgotten technology, but a forgotten level of human artistry and determination. These lingering questions form a constellation of doubt around the official story. How did they achieve such perfect, uninterrupted flatness across surfaces wider than a bus? The sheer scale of these flawless planes defies the very nature of manual grinding. Think of sanding a tabletop by hand until it is as smooth as glass, and then imagine doing the same to an entire driveway without leaving a single undulation or deeper scratch. The abrasive sand method, while effective for removal, is chaotic at a microscopic level. It should leave behind a telltale landscape of random, cross-hatched scratches, a signature of the loose, tumbling grains. Yet on the finest granite boxes, these scratches are often absent, replaced by long, consistent, parallel lines that hint at something far more controlled than a slurry of sand and a wobbly copper saw. This points toward a tool that was rigid, stable, and moving in a single, unwavering path. Then there is the ghost in the machine, the impossible feed rate of the ancient drill. That granite core from Petrie's collection remains one of the most direct and damning pieces of evidence. The drill that created it did not slowly abrade its way down. It bit into the stone with a confidence and speed that our modern recreations cannot begin to match. We are left to wonder what kind of power source could spin a drill with such immense torque, and what the cutting edge was made from that it could maintain its sharpness under such extreme pressure. The core sample is a receipt for a transaction we cannot reconcile, a record of efficiency that should not exist. Perhaps the most haunting question of all is one of absence. Where are the workshops that produced these masterpieces? For a project on the scale of the Great Pyramid, the manufacturing of such precise granite elements would have required an industrial-sized operation. We should be finding vast sites littered with the debris of this work, mountains of granite dust, broken drill bits, worn-out saw blades, and the foundations of the workshops themselves. While we have found some copper tools, we have not found the specialized, heavy-duty equipment that the evidence on the stone implies must have existed. Where are the broken diamond-tipped drills, the frames for the giant saws, or the vats for the mythical softening chemicals? Their absence is a silent scream in the archaeological record. It is as if the technology itself was designed to leave no trace, to pack up and vanish once the work was done, leaving behind only the perfect, polished results as its sole calling card. These are not minor gaps in our knowledge, they are chasms, and it is across these chasms that the most thrilling possibilities are built, driving researchers to keep looking, keep testing, and keep asking the one question that has never been fully answered: how? This single granite mystery threatens to crack the very foundation of our history books. Solving this puzzle is about far more than figuring out how they cut stone. It is about re-evaluating the entire narrative of human progress. We are taught a linear story, a steady climb from primitive beginnings to our current technological peak. But what if that story is wrong? The evidence locked within the granite of Giza and Puma Punku suggests a terrifying and thrilling possibility that human civilization does not simply move forward in a straight line. It can also fall back, forgetting entire libraries of knowledge in a great collapse. Imagine a dark age so profound that it could erase not just an empire, but the very science that built it. We see this on a smaller scale in our own world. The recipe for Roman concrete, a material that could harden underwater and last for millennia, was lost for over 1,000 years after their empire fell. Our own modern society is built on digital data that could be rendered unreadable by a single massive solar flare or a long-term power loss. The knowledge we take for granted is astonishingly fragile. Now apply that fragility to a civilization that built with stone, not silicon. If the pyramid builders did possess a method to soften granite or to harness resonant frequencies, that knowledge would have been held by a small, elite group of master artisans. It would have been their most sacred and powerful secret. A single cataclysm, a prolonged famine, or a violent invasion could have been enough to sever that thread of knowledge forever. The survivors, the ones who rebuilt, would have been left with only the tools they understood, the simple copper chisels and stone pounders we find in the archaeological record. They would have gazed upon the impossible works of their ancestors with the same awe and confusion that we do today, perhaps attributing them to gods or giants. This forces a humbling reconsideration of human ingenuity. We tend to assume that our way, our technology, is the only logical path to advancement, but the granite tells a different story. It whispers of a different kind of genius, one that may have solved the same problems we face, but with an entirely different set of tools and a fundamentally different understanding of the physical world. Their path to precision might not have been through harder and harder metals, but through a deep mastery of materials, sound, or chemistry that we are only beginning to rediscover. The true implication of this mystery is that our past might be far more complex and far more brilliant than we have ever dared to believe. So where does that leave us standing before these silent, perfect stones? The mystery of the copper tools and the granite they supposedly shaped remains one of Egyptology's most captivating enigmas, a puzzle carved from the very bedrock of our history. We have walked through the evidence, from the impossible precision of the serapeum boxes to the ghostly spiral on a broken drill core, and we have listened to the competing voices of mainstream science and radical theory. The official story of relentless pounding and abrasive sand offers a possible path, a testament to almost unimaginable human toil, yet the artifacts themselves seem to whisper of something more elegant, something lost. Was it a secret chemical recipe that turned stone temporarily to clay, a forgotten science of sound that could make granite sing and soften, or simply a level of skill and patience so profound that we, in our fast-paced world, can no longer comprehend it? The evidence does not force a single answer upon us. Instead, it extends an open invitation to keep questioning, to keep looking, and to never fully accept that our current understanding is the final word. The true legacy of the pyramid builders may not be the pyramids themselves, but the relentless curiosity they ignite in all who gaze upon their work. Now we turn to you. What do you think happened in those ancient workshops? Share your wildest, most compelling theories in the comments below. Did they master a form of forgotten chemistry, or was their genius something else entirely? If you want to continue unraveling the secrets of our past, make sure to hit that subscribe button for more journeys into the world's greatest ancient mysteries. The conversation is far from over, and your voice is the next piece of the puzzle.